Okay, for this problem, what we're doing is we're looking at the relative contribution to the incidence of something. In this case, it was PKU, phenylketonuria. The relative contribution of from a population that has a particular inbreeding coefficient, if we can scale that and then sort of use that to predict things. And so in the PowerPoint slide, it said in populations of non-relatives, the incidence of PKU is 1 in 10,000. In populations of first cousins, the incidence of PKU because of inbreeding goes up to 7 in every 10,000, or 0.007. And so here we can see, okay, what is the effect of the inbreeding coefficient on that population? And so then it goes on to ask you, okay, if we looked at populations of half siblings, what would we predict to be the incidence of PKU in population of full sibling matings, of course, and in populations of half sibling matings, what would we predict the incidence of PKU to be? Okay, so what we want to do is we want to say, okay, what is the inbreeding coefficient of non-relatives? And then how does that compare to the incidence of PKU? And so here, F of non-relatives is 0. The inbreeding coefficient of first cousins here is 1/16. And so now we have 0 paired with this particular incidence, 1 in 10,000 in populations with inbreeding coefficients of 0. That's how many you get. In populations of inbreeding coefficients of 1/16, that's going to cause it to go up. How much does it go up? It goes up from 1 in 10,000 to 7 in 10,000. And so what we can do now, they're asking us, okay, other populations, and if we look at populations with half sibling matings and populations of full sibling matings, we also know the inbreeding coefficient of each of those. So the inbreeding coefficient of half siblings is 1/8. So that we can compare these, we're gonna say, okay, or we're gonna put it in a common fraction, and we'll say, okay, that's the same thing as 2/16. And full sibling in populations of full sibling matings, that the inbreeding coefficient in that or between full siblings is 1/4, right? So we also scale that to 4/16. And so now we have paired data. So here, just to make it comparable and simplified, we're going to say, okay, in this column, we're going to do the inbreeding coefficient, but we're going to put X is going to be whatever it is over 16. So 0 is 0/16, 1/16 here of first cousin matings, right? We're just going to have that equal to 1. Also, we're going to put Y over the incidence over 10,000, or the number over 10,000. So here, Y is equal to 1 over 10,000. So we just put 1, or 7 over 10,000, and that just equals 7. And so that makes it a lot easier. So we could actually either do it one of two ways. We could graph it, and I kind of drew out a graph here. You would graph 0 and 1 down here, 1 and 7 up here, and then kind of graph a line and then be able to predict that, right? To do that, we need to get the slope, right? Or we can just use these equations. The slope is y sub 1, the difference between y sub 1 and y sub 2, x of 1, x of 2. And so the slope then is the difference between 1 and 7 over the difference between 0 and 1. That equals -7 or -6 over -1, which two negatives cancel each other out. So it's 6, right? So the slope is 6. So we can come in here and put the slope as 6. B is the y-intercept. So what is y equal to when x equals 0? We see that's 1. Now here we have the equation. And so with this equation, we can plug in any of the y's, right? Or the x's and figure out the y's. And so here, let's just plug in 1, right? So x is equal to 1. 6 times 1 is 6, plus 1 is 7, and so we get it there. And so now we can say, okay, half siblings. Half siblings, the inbreeding coefficient is 1/8 or 2 over 16. Put 2 into here. Plug the 2 into this equation. 6 times 2 plus 1 equals 13. Here for this other one, we don't know what that kind of mating is, but here for the full siblings, right, is equal to 4/16. So the x is equal to 4. Plug the x into here. 6 times 4 plus 21 equals 25. Another way that you can do it if you don't want to use the equations, and this is for me, this kind of seems the most straightforward, is you just kind of look at, okay, going from 0 to 1, you increase by 6. So you're going to increase the 1 by 6, that equals 7. Going from 1 to 2, add 6 again here, that's 13. Going from 2 to 3, we don't know what that inbreeding coefficient is, but just to, so that we can do it in sort of incremental steps. You add 6 here, that equals 19. From 3 to 4, add 6, that equals 25 over here. And so that's that problem. And that's kind of using the inbreeding coefficient to see what the actual sort of real life expectations would be for a particular disease. Okay.